Okay, so we've got our truss number one here. We've got 5 members, AB, AD, AB, AD, BD, BC, and CD are our 5 members. Got those laid out down here. And those are going to be all of our internal forces. But before we can worry about our internal forces, we need to start with our external forces. So we've got our one applied load, that applied force of 45, negative on the X at joint B. Because A is a pinned connection, we will have both a Y and an X reaction forces. We will also at C, because C is a roller, there will be no X on this roller, but there will be a Y. Because they just move freely along that X-axis. Okay, now we need to do our moments to figure out what the what our reactive loads are, reactive forces are, excuse me, on both RAY, RAX, and RCY. So we've chosen to use point A as our pivot point for our moment. So all the moments that we're solving for will be using A as their base. So we're looking at the summation of moments that should be equal to 0. In other words, all of our clockwise must equal our counterclockwise. This all comes down to this is statically balanced. This does not move. If we had a difference in the clockwise and counterclockwise at point A, then this would be moving at this point. If we had more clockwise force on A, this truss would be moving down. If we had more counterclockwise, this truss would be moving up. We don't have those. This truss is staying solid. It's staying in a static position. So we know we are statically determinate. We're not going anywhere. Now let's throw the mathing at this. So first moment we'll look at is moment AB. That's where our applied load is. And so moment AB is going to be our force of 45. That's negative because it's moving. It's going to be moving to the left. So that means that the forces, if we're pivoting on A, we apply on the negative X, it's going to be moving this way. So negative 45. And we need our perpendicular distance. So we're applying our force this way. So we need to make sure that our distance that we're measuring is coming straight up and perpendicular to how the force is applied relative to the pivot point. In this instance, we're looking at a distance of 8 units away from A. So our force is negative 45. Our distance is 8. My magic number box tells me that negative 45 times 8 gets me answer. Negative 45. There we go. Hit the right button and it works much better. Negative 45 times 8 is going to get us negative 360. So this is our counterclockwise moment. So we need to have a clockwise moment at C. Remember, we're still staying anchored at A. So that's the only option we have for our forces being applied on a clockwise motion are going to be the forces here at C. What that tells me is that my assumption of a positive force on the Y is incorrect. If I'm going to oppose the counterclockwise moment from AB, I'll need a clockwise moment for AC. And if that's going to be clockwise, my force has to be going down. So now our moment AC is going to be equal to RCY times our perpendicular distance, which is 9. So we know our force is coming this way. And a perpendicular measurement away from A is going to be at 9 units. and that's going to need to equal 360. Manipulate this around. That's going to tell us that 360 divided by 9 is going to get you 40. And actually, I missed a measurement that should have been negative 360 divided by 9. Negative 40. I need that to remember that's negative 40, because remember, our RCY has to be pointing down. So that measurement should have been coming back as a negative measurement. So let's enter in our information we've got. Force B at the X is minus 45. We know that RCY is going to be negative 40. So we still need to solve for RAX and RAY. So RAY will be the, well, we'll start with RAX. There is nothing being applied on the Y directly. All we're looking at here is the X, which means we need to look at what our lefts and rights are doing. Remember that all of our rights need to equal all of our lefts. In this case, the only left force that we have is our applied force at B is going to the left. So RAX has to be equal and opposite to that applied force. So RAX must be a positive 45. RAY, on the other hand, must be a counter to RCY. Again, equal and opposite forces. We know that RCY is negative 40, so that means that RAY must be a positive 40. That's the only way to balance this out. So now all of our clockwise equal all of our counterclockwise. We figured that out to get us RCY and our moments. Then with all of our lefts and rights, we see that our force applied at B is negative 45 on the X. So the only way we can counter that, looking at this drawing, the only location that can counter the force on X is here at A, at RAX, and that's going to push the opposite direction, getting us the positive 45 at RAX. All right, so we have all of our ups and downs equal. There's our ups and downs. All of our lefts and rights are equal out, and all of our clockwise and counterclockwise equal. All of our external forces are figured out. Now we can move on to our internal forces. And when it comes to internal forces, sorry about that. When it comes to our internal forces, so we need to start laying out our free body diagram and doing our method of moments, our method of joints to balance everything out. So we can draw out our free body diagram, and you're going to want to use arrows, not just lines, while laying this out. One of the really nice things that Notability does for us is I can draw, put an arrowhead and hold, and I'll get an arrow. We want to draw all of our joints so that they are in tension. That's one of our primary assumptions, is that all of our joints are in tension, which means every one of them is being pulled on. So our arrows are going to be drawn moving away from the joints. So there's our joint A. And when we get to joint B, so B is also in tension for all of its, that's our assumption. Go. That is joint B. And then we've got joint D. Going up. And then we've got joint C. I'll label that. We need to put in our angles that we know. So we know this is 69.444 degrees. And we know this is 53.13 degrees. Now I also need to put in my reaction forces and my applied load. And I like to use red for those just to visually separate them out from the members. And we determined that RAY positive 40. So coming up. And RAX is a positive 45. Last but not least, we've got RCY, which was a negative 40. All right, so that's all of our knowns, and we can pick one joint to work from. I like to start at my pinned joint, which means I'm going to start with A. So I'm going to take and copy that. And I'm actually, just to make it easier if I need to print this later, I'll grab all of this, slide it below the page break. And let's post up for A. All right, so we've got all of our knowns labeled. I just want to change and include the names of the members so we know what we're working with. So when it comes to our method of joints, we've gone through, we know all of our externals for our internals. All we're caring about right now is that the summation of forces on the Y are equal to 0, and the summation of forces on the X are equal to 0. So let's get started. I like to start with the Y. I have no idea why. I simply do. In this case, for this joint, we have equal information on X and Y. If we only had one or the other, that's where we would start. But because we have both, dealer's choice, I'm going with the Y. So I need to figure out what all of my forces are on the Y. And that's equal to 0. So let's see. I've got my RAY. And I have the Y aspect of AB. That's all that I have acting on my Y. So I look around, I've got U, and I've got the Y part of U. That's it. We know that's equal to 0. Now I can put in my known values. So 0 equals, we know RAY is positive 40. And we make the assumption that because joint A is in tension, that means that AB is pulling away from that joint, and the Y aspect of A would then be positive. So moving up on the Y axis. So 40 plus ABY. Now this Y here is just is a placeholder. This is shorthand because this is looking at our component vector formula, where if we wanted to find the force on Y is equal to force times the sine of theta. This is shorthanded there just as the letter Y. Okay, so don't be thrown off by it. This is the formula we were using before when we were doing our vector components. So this has not changed, just a little bit of a kind of a shorthand there. So if I rewrite my formula, 0 equals 40 plus AB times the sine of theta. And in this case, theta is 69.444. And now we can manipulate our formula here. So if I subtract 40, I got negative 40 equals AB times the sine of 69.444 divide by the sine of 69.444. Same thing on the other side. So we've got negative 40 divided by the sine of 69.444. And that is going to yield us negative 42.72 equals AB, which means that AB is equal to 42.72. And we got a negative, so that means that our assumption about this joint being in tension was incorrect. So this is actually in compression. So what I'm going to do is I'm going to come up here, and I am going to invert my arrow. I know this is in compression, so I want my drawing to reflect that as well. And I like to color code for compression to blue. Why? Don't know why. Because blue is an easy primary color probably, and it's an easy one that I have stored and don't need to worry about it. So I will tend to use red for my members in tension, blue for my members in compression, both when I label them on my drawing as well as when I fill in my table. And I now have additional information, so it's time for me to update my table. Copy. Paste. So what I have just solved for is I've just solved for the force that's on AB. I know the direction that it's moving in. It is compressing against my joints. And I know that the actual force itself is 42.72. So I'll change over to my blue. Compression. So that is the sum of our forces on the Y. Now we can look to our forces on the X. We know that's going to equal 0. We know that force on the X is equal to our force times the cosine of theta. And our force, we have already figured out. The force on member AB is 42.72. So just keep that in the back of our mind when we go and we need to reuse this formula as we go through the summation of the forces. We can replace AB with 42.72. It's a known for us now. But let's look through all of our forces on the X. So on the X, we have our positive 45 for RAY. Let's label that our forces are RAY. And the X aspect of AB. Now, we figured out in the last step that AB is in compression, which means it's going to be pushing, the sense is down and to the left. So if we're looking down and to the left, that means that the X aspect of this, we're moving to the left, so the X is negative. So we're looking at summation RAY minus ABY. And we've also got AD on here at the same time. And we're still operating under the assumption that AD is under tension. So we're going to assume that this joint is pulling away, this member is pulling away from that joint. plus AD. All right, rewrite with our knowns. 0 is equal to RAY, which is going to be 45, minus 42.72 times the cosine of 69.444 plus AD. All right, let's try and get AD isolated here. So minus 45 equals 42.72 times the cosine of 69.444 plus AD. Answer times cosine 69.444. I'm going to call that 15. So we have negative 45 equals negative 15 plus AD plus 15 plus 15. That gets us negative 30 equals AD. So that tells us that AD is 30, and our assumption was wrong again. AD is also in compression. So let's take and let's update our drawing here. Blue, spin it around. I'll do the same up here. And change my color. Last up is getting that into my table. Oh. And now we know that AD is 30 in compression. All right. That is the extent of what we're going to find from joint A. So now we can move on to our next joint. I would like to move over to C because, again, it has the fewest unknowns remaining. If we look at B, we've got 2 unknowns and 1 known. On C, we'll be able to work through with our forces, and because we have the known of our angle, makes life just one step simpler. Okay. Now we're going to move on to joint C. I'm going to scroll on up, and I'm just going to copy and paste. Just be careful when you're laying these out. If you're copying and pasting, make sure you really are sure with what you have. It's very easy if you were to have some incorrect information to begin with. If you just keep copying and pasting, you're going to propagate that error along the way. But that's also part of why I always want you to show me your work, so I can see what you're doing and try and make some sense and track back where the mistake might have been made, not that the mistake had been made. Let's label these CD, BC. So, summation on the Y. There, we've got RCY, and we've got the BC aspect on Y, and that is negative RCY. Let me fix that. We know that RCY is, its sense is down, so that tells us that it's negative on the Y. So negative RCY. But if we look over here at BC, that sense is up and to the left, which tells us that that's going to be a positive for BCY. Now we plug in our knowns. 0 equals negative 40 plus BCY. Remembering that Y is just that shorthand for force times the sine of theta. I'm actually going to take and color code that nice and whoop. Red. Bigger letters. Blow it up. Don't forget it. Add 40 to both sides. 40 is equal to BC times the sine of 53.13. Gives a nice even 50. So BC is equal to 50, which tells us that we are in tension. Our assumptions were correct. So BC is equal to 50 in tension. And so I'm going to take and make U red. And it's time to update my table again. So we now know that BC is 50 and in tension. All right. All right, so let's take a look at joint C. We've already got our summations on the Y. Now it's time for our summations on the X. No, not Y. That's equal to 0. So 0, all of our X forces. Let's see. We've got CD, which is moving back. We are assuming we are in tension, so that's going to be pushing to the left. So that's negative CD. And if we look at BC, we know that BC is in tension. So it's pulling away from this joint here. So that is moving, again, to the left on the x-axis. So that's negative CD minus BCX. There is no RCX because it was on a roller. So these are all of our forces. Now remember, this X here is our shorthand, or force on the X is equal to force times the cosine of theta. So 0 equals negative CD minus the force of BC times the cosine of theta, which is 53.13 degrees. We'll add CD. CD is equal to negative. BC is 50 times the cosine, 53.13. And our magic number box in here. And it tells us right there, 50 cosine 53.13 gets us 30. But it should be negative 50. Let's flop this around, sorry. So this should be, let's get that calculator back in here. Negative 50 times the cosine 53.13 gets us negative 30. CD equals negative 30. So that tells us that CD is equal to 30 in compression. Update my color. Blue. And going to come over here, and we've got 30 in compression. Last up is BD, and this is one that we can do with some nice logic. We don't need to worry about doing a whole lot of mathing here. So if we look back here at our original joint at D, let's lay out joint D here, copy over. So our forces on D, we know that CD is 30 in compression, and we know that AD is 30 in compression. So our arrows should be swapped here. But we have no forces that are acting on the Y. If we look back at our original drawing, on B, there is no X aspect to this force. This force is only moving on the X. So none of these forces are going to be applied here on BD. BD has become what's known as a zero force member. So BD is equal to simply 0. And that, my friends, finishes off our chart, finishes off our whole process here. So key things keeping in mind, looking at your ups and downs, lefts and rights, counterclockwise and clockwise all need to balance out. Clockwise equals counterclockwise. Up equals down. Left equals right. All those work out. That's going to get all of our external forces. When it comes to looking at our internal forces, the big pieces we're looking at, summation on the Y has to equal 0. Summation on the X, do that every time, has to equal 0. And if we're looking at any joint, or excuse me, any forces that are moving on an angle, so finding the X aspect is going to be equal to the force times the cosine of theta. And we're looking at force on the Y is our force times the sine of theta. Those are the formulas you're going to use over and over and over and over and over again. Oh, last one we forgot. We would come across that one before we're worried about those summation of forces is our moments. That our moments, our summation of moments equals 0. And that really comes in with these 3 right here. You pick one joint as your pivot point for your moments. Once you solve for that, you move on to your free body diagram. After you have your free body diagram written up, then you start worrying about your summation of your forces on X and Y for each aspect of that joint. Any questions, please send them my way, and we'll get this all knocked out. Thanks for your patience getting this up, everybody. I will talk to you guys next week.